All right, so welcome to our first lecture of things you really need to remember about thermodynamics for process design. And so this is a review of the first three chapters so far of this book, Introduction to Chemical Engineering Thermodynamics. Sixth edition by Smith, Van Ness, and Abbott. And so some important things to remember about the basics of thermodynamics are that the ways we're going to be using it in design are for calculating heat and work requirements, for chemical and physical processes, also for determining equilibrium conditions, for chemical reactions, and then finally to determine equilibrium conditions or transfer of chemical species between phases. So it does not give you any information about the rate of chemical or physical processes. Rates depend on driving forces and resistance, but it does tell you things about equilibrium conditions. So whenever we're doing thermodynamics, we like to identify a system that we have under consideration. Important things include, this talk's going to be a little bit interesting because, as I said, I'm just reviewing things that I have found are really important from thermodynamics to talk about process design. And so it's going to feel a little scattered because there's going to be a lot of ideas where it's sort of the hint, like, remember that, and then kind of move on from there. But so work is an important concept, and it's going to be performed whenever a force acts through a distance so in the notation of differentials, it will be dW equals F dl. And so F here is going to be the component of the force acting along a line of displacement dl. And so, for example, if you have a fluid in some type of cylinder, and then this lid is moving up and down, like there's a piston, and so as this lid moves down, then the fluid gets compressed. As it goes up, the fluid, maybe it's a gas, gets expanded. And then, so the force exerted by the piston on the fluid equals the piston area times the pressure of the fluid in this scenario, and the displacement of the piston is the total volume change divided by the area of the piston So dW is going to equal negative pressure times area. So we said that this is that force. It's the piston area times the pressure of the fluid times D of the volume divided by area to get the DL. So because we assume that A is constant here, these two are going to cancel out. And so we're going to end up with dW equals negative P dV total, or that the work is going to equal the integral, the negative of the integral of V total V1 total to V2 total of P dVt. So really quick, let me talk about why the things on this slide are important for design. So first is it's important to understand your heat and your work requirements when you're doing process design. If you have to do work, for example, or if your process produces work, that's related to money, because if you have to do work, you're going to have to provide some source of energy. So you're going to, in some cases, either buy electricity, or you're going to have to make electricity, or some other source of energy to cause the work to happen. If your process makes work, maybe you can sell that back as electricity. So very important from a monetary perspective. Also with heating requirements, also very important from the same reason. You're going to need utilities that are either going to provide heat or remove heat. And so again, that's important for understanding your costs of your utilities. Determining equilibrium conditions for chemical reactions. That's important if you need to understand the design of your reactors. Equilibrium conditions for transfer of chemical species between phases. That's super important because a lot of operations that go on in chemical processes, like distillation and flash and different things, involve approximating those at the design stage as being in equilibrium on, for example, different trays for distillation or within a flash drum. And then that's then important for predicting what the compositions of different streams that are being assumed to be in equilibrium are. Okay, so that's why thermodynamics is very important for process design. In process design, we're primarily concerned with steady state operation. And so these types of constant properties are very important. The reason that I bring up this one about the work is because it is helpful for better understanding things about why you have higher costs for compression of a gas than if you're pumping a liquid. And that's because volume changes for your gas are going to be more significant because gases are much more compressible than liquids. And so therefore, as you can see here, the changes in the volume are going to impact how much work you have to do. Okay. Next thing we're going to talk about is in the second chapter. So it's the first law and other concepts. So this is the second chapter of that book. So I think some important things are just remembering your lingo. So for example, internal energy. This is the energy of molecules internal to a substance. It doesn't really have a concise thermodynamic definition. Its absolute value is not known, but we only in thermodynamics generally need the changes in that quantity, so that's fine. The first law of Thermo is used in process simulation all the time. This is that energy is conserved. You can do energy balances for different types of systems. That's actually Aspen Plus runs on this. It runs on doing the energy and the mass balances into and out of the different units. So it is important people understand energy conservation and the ways that that makes equations. So another really important thing for understanding how Aspen Plus works is the idea of degrees of freedom. So I'm going to write this statement. So for a homogeneous pure substance, fixing two thermodynamic properties, so for example, temperature, pressure, specific volume, so density here. which is the volume per molar per mass, fixes others and determines the thermodynamic state. Note here it says homogeneous and it needs to be a pure substance. Then, so this 2 is important for that case. If there are things like you have multiple components, so it's not pure and stuff, this is not going to be only 2 thermodynamic properties. But so for example, say that you have nitrogen at 300 K and 1 bar. So now that fixes the specific volume or density and fixes the molar internal energy. So energy per mole, or internal energy per mole, I should say. Okay, now, so that sounds like great. You can remember then that if you have a homogeneous pure substance, you need to fix 2 thermodynamic properties. It fixes the rest of the thermodynamic state. Okay, so what is it if I don't have a homogeneous pure substance? Okay, so let's just consider still the case of non-reacting systems. So non-reacting systems at equilibrium. The phase rule says F equals 2 minus pi plus N. So what does that mean? So F here is the degrees of freedom. Pi here is going to be the number of phases. And N is going to be the number of chemical species. So for example, the number of degrees of freedom of liquid water in equilibrium with its vapor is given by F equals 2 minus pi plus N. So this is going to be 2 minus, so number of phases. In this case, there's 2 because it's liquid in equilibrium with the vapor, so 2 phases, plus N, so there's only 1 component here, it's just water. So this gives back 1. So what that means is that if I fix 1 thermodynamic property here, I have fixed the thermodynamic state of this entire system. So really quick, why does this matter? Okay, so for design, why does this matter? So one thing is in Aspen Plus, you're going to see that it's going to oftentimes require you to put certain numbers of things. So for example, if you have a stream flowing in to a unit in Aspen Plus, you're going to, in general, see that when you put your input, it's going to require you to do something like temperature and pressure. And then you're also going to have to specify the species composition and then also the flow rate. And sometimes you'll be able to specify something else like vapor fraction. But note that the reason that it asks you for a certain number of things is because it needs to fix the thermodynamic states. And once you fix a certain number of things, you're able to fix the thermodynamic state. And then, so also know this is actually really important, what's going on here with regard to steam tables, or I shouldn't say steam tables. What I should say is the levels of steam you have at your plant for heating and cooling, which is utilities. So the reason that this is really important is because we're going to be talking about, when we talk about steam, we'll say a certain pressure of steam is available at this plant for heating. And then when, not cooling, sorry, I think I said cooling, but so say that we have a certain pressure of steam is available for heating, then if you think of it like this, if that steam is saturated, so it's approximately at thermodynamic equilibrium, it's just right at the point where already all of the liquid has gone away and it has just become totally vapor. If you imagine you're approximately at that state, then as you can see, you specify one part of the thermodynamic properties and that fixes all the others. So if I tell you a blank, blank, blank pressure of steam and it's saturated steam, so it's effectively at equilibrium, I only have 1 degree of freedom. So knowing the pressure of that steam automatically fixes everything else, including temperature of the steam. That's really important because when people are talking about pressures of steam for heating, that might sound really off base at first because you think, well, I don't like pressure isn't what heats. Temperature differences are the driving force for heat transfer, not pressure differences. Why does this matter? Well, it's because the steam is saturated. And so if you specify its pressure, then you have effectively specified its temperature because of this phase rule, meaning that now you have specified the driving force for heat transfer, which is the temperature. Okay, other important things for design is going to be a reversible process. So this is a process is reversible when its direction can be reversed at any point by an infinitesimal change in external conditions. So let's go back, for example, to that equation we saw earlier. So this one, the one for the work. So the work done on the system is given by this equation only if the system is no more than infinitesimally displaced from a state of internal equilibrium. So assuming that the work is actually given by this equation, implies the process is reversible, process of performing the work is reversible. And so you could say, how do I know that? Well, it assumes, if you think back to how we derived that for the cylinder with the piston, it assumed that, for example, that the pressure is uniform throughout the fluid, so that the force of the fluid on the wall is equal to the pressure times the area. And so if there are pressure differences, if the pressure near the wall is not the same as like some type of bulk pressure that you're measuring, then maybe you're not calculating the force correctly. So for reasons like that, this kind of already assumes that the process is reversible. So in general, we don't really have reversible processes in real life. So what you need to do is usually for a real process, which we're talking about real stuff now, this is process design, we're going to talk about designing real things. So usually you calculate work for a reversible process and use an efficiency to estimate the work of a real process. So let me clarify why that's important. This is important because we are dealing with real processes where real work is being done. So we're going to have things like compressors, turbines, pumps, different things where work is actually important. And so you'll see in Aspen Plus that there are ways of adding an efficiency to help account for irreversibilities that are inherent in the process to get a better picture of the work. And so let me make a statement about this. So the work of an irreversible process is calculated in 2 steps. I'm taking this verbatim from the Smith, Abbott, and Van Ness book. So 1, the work is determined For a mechanically reversible process, that creates the same change of state. So change in the thermodynamic state as the actual irreversible process that you're going to carry out. And then 2 is going to be that you multiply or divide the work by an efficiency to get the actual work for your process. And how do you know if you're going to multiply or divide? So you're going to multiply if you produce work with your process, and you are going to divide if process requires work. Okay, so let's clarify why. So if you are going to produce some work, then that's like positive benefits for you. So you are going to need to multiply it by this efficiency, which is less than 1, to say, actually, you're not going to get all the work you ideally think you're going to get. If instead you are going to need to do work on your process, so maybe you have to do compression, for example, and then that is like a cost to you. So the more compression you have to do, the more costly it is because more energy you need to do it. So in that case, you're going to have to divide by this number, this efficiency that is less than 1, which is going to show an increase in the amount of work that you're going to have to do in order to achieve the same effect. So as you can see, the efficiencies do not work in your favor. Either they make it so that you don't make as much work as you think you're going to do, or that you have to do more work than you had hoped. Okay, then a few more things. So important thing to remember is the definition of enthalpy. I think it's very interesting that this textbook frames it like this. A lot of the things I'm writing have been direct quotations, but I'm going to quote this one because I find it particularly interesting. The mathematical and only, that's the part I find interesting, definition of enthalpy is H equals, or is defined as U plus PV. And this is going to be H, U, and V in molar or per mass units. So either way, this could be either enthalpy per mass, internal energy per mass, and then volume per mass, or enthalpy per mole, internal energy per mole, volume per mole. So it just has to be consistent across the board here. But I think that this is really helpful because I think when I was in thermodynamics, I think I thought that somehow enthalpy was this mysterious quantity that I was just having trouble to visualize. But I like this, the mathematical and only definition of enthalpy, saying, yep, the definition of enthalpy here is from pure math. So I think that's very helpful. And so, yeah, so enthalpy is definitely important because enthalpy is involved in the different streams. So when you do mass and energy balances, which is definitely what Aspen Plus is running on, then this is going to be important to remember your enthalpies so that you're able to remind yourself how Aspen Plus works. So now, brief finish here with chapter 3. So this is about the volumetric properties of fluids. So in this chapter, there's a lot of things about different equations of state. It is important to remember your equations of state and to go over them, to go over your different thermodynamic relationships when you're trying to choose in Aspen Plus your property method, because it's important to remember that each of them has benefits and limitations. So for example, ideal gas, okay, that assumption might be all right if you're dealing with really low pressure gases, but at higher pressure, that's going to give you terrible predictions or not so good predictions. I don't know how terrible it is. I mean, it kind of depends, but potentially not as accurate predictions. So you're going to have to choose the property method that's right for your process based on having an understanding of how these thermodynamic models, none of which is perfect, like what their limitations and their benefits and their ranges of applicability are. And that again is an experimental thing. So it will be that people have tried to systematically develop these relationships, equations of state, and other property methods based on having observed some experimental data. And they try to fit it and say, oh, it appears that this relationship approximately captures the data that I have over these ranges or for these types of compounds. And then they publish those as ways that you can try to approximate what the properties are of things when you don't have like experimental data. So it's kind of a fit of the experimental data in some sense, which is really helpful for performing mathematical calculations. And something like Aspen Plus for sure uses property methods in calculating a lot of important quantities that you need for actually solving. And so that also brings up an important point that if you choose the wrong property method, all of your calculations are not going to be representative of the physics of the process. And so some things like internal energy, enthalpy, etc., from which we get the heat and work requirements of our process. So where Aspen Plus is calculating like your heat transfer and the work you have to do and stuff, those are coming from things like internal energy and enthalpy in the mass and energy balances. And the internal energy and the enthalpy in Aspen Plus are being calculated based on the property methods you choose. So if you choose the wrong property methods, really your whole process is messed up. So it is very important that you choose the right things, or else, like, you know, Aspen Plus isn't going to tell you, oh, you chose the wrong property method, this doesn't match thermodynamics, this doesn't match thermodynamic data. It doesn't know that. It's relying on you to tell it that. So something that is a little bit important here is that people remember their pressure, volume, and temperature type relationships. So here's a PT plot. I put this one up here because it's a good reminder of the way that fluids function. So this just reminds people of some good points. So there's like a solid region up here, which is at higher pressures and lower temperatures. Then we have this sublimation curve here, which is where you can go from solid to vapor and back again. Then we're going to have here the triple point. The triple point is where all three phases coexist in equilibrium. It has a certain temperature and pressure, and you would find if you use the phase rule that there's like no degrees of freedom here. So this happens at a certain temperature and pressure, and that's it. If you're at that temperature and pressure, you're at the triple point. If you're not there. Then there's this fusion curve over here. That's going to go between the solid and the liquid phase. Here's the liquid region. And here we have our critical point, which is important because it's where there stops being some of the normal distinguishing factors between the vapor and the liquid. This is the vaporization curve. And here is the vapor region. So that just should remind you of your basics of your thermodiagrams for a pure substance. And so thanks so much. That was the first installment here of what thermo you need to remember in order to do process design.